We're now beginning session 3 on water quality. And we will pretty much have the same format that we've had before. So our speaker for water quality is Hugh McCready. And we may have neglected to mention before, he works for Pito Associates. And he's working on the Pebble project. And I don't think I need to say much more if he's ready. If he's not ready, maybe I'll say a few more. Okay.
Yeah. Thanks, Kirk. So now that we've talked about the physical flow system, I'm going to spend a little bit of time dipping into the groundwater and surface water quality programs that we've conducted for the Pebble project. Now, there was quite a large team of people that were involved in this project, and I just want to take a minute to acknowledge them. SLR Alaska was responsible for all of the groundwater sampling. Also, Mark Stelgis of SLR was the person who was responsible for putting all the surface water quality data together and doing that interpretation and writing up the that section 9.1 of the environmental baseline document. And of course, Schlumberger Water Services was involved. Myself, our two consultants had some input. HDR Inc., Shaw Alaska, and the Alaska Peninsula Corporation have all contributed to this rather large undertaking of characterizing the groundwater and surface water quality throughout the study area for the Pebble project. So my profound appreciation, particularly to the sampling teams who went out under a whole range of conditions, including the wintertime, and continued to collect good quality samples. So the analyses that we did for the quality characterizations included what I call index parameters, which included total dissolved solids, dissolved oxygen, pH, and temperature. These parameters generally give us the big picture of what the water quality is like. We also analyzed for major ions, calcium, magnesium, sodium, potassium, the cations, alkalinity, sulfate, and chloride representing the anions. So these constituents are representing the bulk of the solids that are dissolved in the water. And of course the total and dissolved trace elements, things like arsenic, copper, iron, all of those kinds of elements. Then the nutrients, reduced and oxidized forms of nitrogen, a couple of different forms of phosphorus, and finally the cyanides. Well, maybe not finally the cyanides. Also selected organics. So the overall water sampling objective then was to characterize the baseline surface water and groundwater quality. And what we wanted to do was to get an idea of what the spatial distribution of the water quality is like, and also get an idea of what the seasonal variation is like. So in my talk today, I'm going to talk first of all about the groundwater, then I will talk about the streams, then a very brief overview of the seeps, and a very brief overview of the pond sampling. Then after I've finished those 4 areas, I will wrap up with an overall summary. So you've seen this picture a few times, or a variation of it. We're looking at 3 separate drainages here: the North Fork Cock-Toolie River, the South Fork Cock-Toolie River, the Upper Tulare, these being the 3 main drainages that have been examined in our studies. But there's also been some sampling down in Cascanack Creek. And again, just to orient you one more time, Frying Pan Lake is about in this area, and then this yellow outline here, this is a description of the general ore deposit area. So starting off with groundwater sampling, as I was mentioning, I've zoomed in a little bit in this map. And again, this is the North Fork Koktuli, the South Fork, and Upper Tulare Creek is over here. Again, this is the general deposit area in the middle. And each of these red dots represents a groundwater sampling location. In other words, what I'm describing as a well nest. So we have most of our locations are what I'm calling shallow installations up to 200 feet. So we have 21 of these locations, and in total we have 25 wells completed in overburden and 14 wells completed in bedrock. And we have one deep installation that Rod was referring to earlier to 4,000 feet. We have one location and 8 monitoring zones. So this is an example of a monitoring well nest. This is the one called MW1. And we've indicated different depths of installation with the subscripts D, M, and S standing for deep, medium, and shallow. So these subscripts are intended to represent relative depths. They're not representing absolute depths, but relative depths. So in other words then, the one that's marked as D would be the deepest one, the one marked as M would be in the middle, and the one marked as S would be the most shallow one. So this is the team out there in the wintertime, and you can see what I meant about heroic undertaking. And one of the reasons I put this slide up is that there's a number of aspects of groundwater sampling that I consider extremely important. And the thing that I liked about this picture is that you can see those aspects even under very adverse conditions. So it's all represented here in the setup that they've got for their groundwater sampling. So the things that I like about what they're doing are the inline filtering for dissolved metals. So this is done in the field rather than afterwards, and it's also done in line rather than being done in a separate container. We have a water level meter to control the micropurging technique that we used for collecting the groundwater samples. There's a sealed flow-through cell for measuring pH, dissolved oxygen, and conductivity. And for the pH and dissolved oxygen, this is a particularly important piece of equipment to have the measurements of these field parameters represent the pH and dissolved oxygen that are in the groundwater system. And then finally we have coolers for transporting the samples back to the base and for transmitting them to the laboratory. The deep groundwater sampling setup at GH8417 is located on the edge of the ore deposit, and the sampling setup there is a little bit different. It was an airlifting setup which has water being discharged out of a spout like this, and the groundwater samples were collected from this discharge. Consequently, our measurements of pH and dissolved oxygen there in these samples, we're not representing those, or sorry, we're not expecting those to represent in situ conditions, but most of the other parameters would be okay. So I'm going to dive into a little bit of the interpretation of the groundwater quality data now, and as I'm proceeding through the discussion of the groundwater quality, I'm going to be doing just a quick description of the types of plots that we're using to do the data interpretation. So this is an example of a cumulative frequency plot, and what we do is we plot the concentration along here and the percentile along here, and this would be an example of a data set. And the way it works is that, for example, this point of the distribution means that 75% of the samples have a concentration of 155 milligrams per liter or less. And then by extension, 25% of the samples, which is the rest of them, would have a concentration of 155 milligrams per liter or more. And I like to use these types of plots to just look at the very big picture. And that's going to be the theme of my discussion of groundwater and surface water quality today, is to look at the big picture, because we don't really have time to drill down into the details. So what I'm doing here with these plots typically is distinguishing between two sets of groundwater samples. One set of groundwater samples from the bedrock and another set of groundwater samples from the overburden. And so then the blue is representing the overburden, and the red is representing the bedrock. And so what we're seeing here is that at lower concentrations, the bedrock samples are very similar to the overburden samples. In the intermediate range, we find that the bedrock concentrations are higher. And then there's those very few samples right at the top of the distribution where the overburden samples have higher concentrations. Another method of evaluating data that we use is something that's called a box and whisker plot, where concentration is plotted along the vertical axis, and we plot a box representing the concentrations of the complete population of a particular monitoring point. So the previous method was looking at all the data together. The box and whiskers plot is now starting to drill down a little bit more and to look at individual monitoring points. But instead of looking at every single data point that was collected there, we look at percentiles again. So the bottom of the box represents the 25th percentile, the line represents the median, and then the upper part of the box represents the 75th percentile. And then we have whiskers on there that represent the 5th and 95th percentiles respectively, and then dots to represent the minimum and maximum. So just to give you a feel for how you might look at one of these plots, what I'm showing here is a relatively long box showing that there's quite a lot of variability in the concentrations, and I'm showing that the maximums and minimums are close to the 5th and 95th percentiles. So it's indicating that in this particular example we don't have any wild concentrations that are much different than the majority of the population, and at the same time we still have some fairly variable concentrations. This, on the other hand, is indicating that for the most part the concentrations are not very variable, but we do have this one sample here that's kind of stands out as being quite different. And then what we have here is a small box, and we have the dots close to the whiskers, and so then this is suggesting that we have very uniform concentrations in that example. So that's a rundown of the way that we use that plot. So now let's look at some actual data. And the reason I like these plots is because it simultaneously gives us an overview, but also if we want to squint a little bit more and look more closely at the plot, then we can also get into some detail. So this is total dissolved solids, and I've distinguished the overburden from bedrock, and you can see that all of the sampling stations are located along this axis. I know you can't read any of those labels, but I'm really not intending you to, because I want to just be giving the big picture. I also have color coding here, where the blue is representing the North Fork Cockatoolie, the orange is representing the South Fork Cockatoolie, and the green is representing the Upper Telerik. And so you can see some differences and similarities between these two data sets for total dissolved solids. One of the things you'll notice is that a lot of the concentrations for total dissolved solids are in the range of 0 to, well, not 0, in the range of 20 to 100 milligrams per liter. And then you'll also see that there are certain locations that stand out from others. So in particular, we have wells MW5M, 5D, 14D, SRK2, and SRK3, and then finally MW12S that are standing out as having concentrations that are higher than the majority of the wells that we're sampling. And most of these wells, except for 14D, are located in more or less proximity to the ore deposit. So this is what they look like here. The general ore deposit area is up here, and so this is MW12, SRK2 and 3, MW5, and then a little bit further downstream around the corner is MW14. Now I want to talk a little bit about influences on groundwater chemistry. And I'm just looking at a simple cartoon here of some typical groundwater flow paths where we have different points along the flow path where groundwater will be infiltrating. And I'm just looking at a scenario where we might have an upper aquifer separated from a lower aquifer by an aquitard. So what I'm talking about here, this is kind of groundwater lingo. What I'm talking about here is maybe some sands and gravels in the shallow horizons, maybe some silts and clays here, so they don't conduct water as well, and then some sands and gravels in this lower horizon here. So what happens then is that we'll have, at this monitoring point, we'll have a shallow flow path intersecting this monitoring point here, and then if we have a deeper completion, then it'll actually be sampling water that was recharged way back here, and it has a longer flow path. So what determines the groundwater chemistry at this monitoring point, both shallow and deep, will partly be the source chemistry. So, for example, water that is recharged far down the South Fork Cockatoolie away from the ore deposit could have a different source chemistry than water that's recharged up close to the deposit, just because of some geochemical processes that might be occurring in the bedrock outcrops close to the ore deposit. Another influence will be reactions with aquifer and aquitard materials along the groundwater flow path. So, for example, if we have an aquifer that has a lot of calcite and dolomite in it, then that will result in a different chemistry here than if it's a flow path where it's primarily, primarily silica sand or something like that. So at this sampling point then, what we might see is some dependence of depth for the groundwater chemistry. So if we're looking at two sampling points A and B, if we're looking at an example where we have ions released to the groundwater as a result of carbonate dissolution along these groundwater flow paths, we might get a concentration profile that looks something like this. Because we have a longer flow path for this deep sampling point, then there's some potential for the concentration at the deeper point to be higher than at the shallow point. So how does this pan out when we actually look at the data that we've collected at the Pebble project? And what we find, I just want to point out that this is a logarithmic scale, so that this tick here and this tick here, this is representing a factor of 10 increase in concentration from 10 to 100, and again this is another factor of 10 increase in concentration from 100 to 1,000. And we did that only because we wanted to be able to illustrate the trends at a wide range of concentrations. That's the only reason I plotted it this way. The logarithmic scale allows me to see what's going on at these lower concentrations while also simultaneously seeing what's going on at the higher concentrations. So, the controls on groundwater chemistry are multiple, and so we don't always see a consistent trend, but certainly there are lots of situations here where we are seeing higher concentrations at depth than we are in the shallow monitoring zones, and so then that's suggesting that the dissolution processes along flow paths are having some influence on the groundwater chemistry at the Pebble site. Now, another example of total dissolved solids, or TDS, versus depth came from the deep groundwater monitoring that we did in DH8417. And you'll see that the first two monitoring ports have TDS values that are very comparable to the shallow monitoring wells. And then what you notice is when we get down to greater depths, below 2,000 feet, then we're looking at TDS values that are ranging from about 1,700 to 2,300 milligrams per liter. So clearly we're into a different kind of groundwater quality when we get down to these kinds of depths at this monitoring point within the general ore deposit area. So that was a bit of a rundown on total dissolved solids, and I'd like to move on and talk a little bit about dissolved oxygen. Again, starting with the big picture, what we observe is that at the very low end and the very high end of dissolved oxygen concentrations in groundwater, the dissolved oxygen content is very similar. But in the intermediate ranges, the vast majority of the intermediate range, we see that overburden has a higher concentration than the bedrock does. And again, taking that approach of looking at concentration versus depth. With oxygen, it's typically the opposite sort of trend that you would expect to see in terms of total dissolved solids. The reason is that it's typical that along a groundwater flow path that there will be different kinds of materials such as labile organic carbon or perhaps trace sulfide minerals that will consume the oxygen. So it's not unusual to see dissolved oxygen concentrations decreasing with depth when you're sampling at a single location. The deeper samples representing water that has traveled further than the samples that you collect from shallower depths. So it's quite interesting at the Pebble site because there certainly are those locations where you see these decreasing concentrations with depth. But the one thing that we were not expecting but have become comfortable that it's a reality is that there are other monitoring locations where there really is very little or no decrease in oxygen concentration with depth. And just to illustrate this with a couple of locations, MW5 and MW8, what we notice is that for example, the MW5M location is representing a place where we do see decreasing oxygen concentration with depth, and it's in a confined aquifer system. In contrast with MW8D, where we don't see decreases in concentration with depth, it's an unconfined system. So the fact that it's confined or unconfined is not quite getting at the heart of the matter. What I'm really getting at here is that this is a very clean material, and with this uniform sort of concentration distribution with depth, it's suggesting that there's really very little or nothing in this material, such as organic carbon or trace sulfide minerals, that's consuming the oxygen. In contrast, this is what I would call a relatively dirty environment, or in superficial geology terms, it's more of a glacial lake environment, and it appears that there are trace quantities of materials that are causing the oxygen to be reduced and to be consumed from the system. So that's total dissolved solids and dissolved oxygen. Let's take a minute and take a look at the pH. So here again doing the cumulative frequency plot, and keeping in mind that pH is a logarithmic parameter itself, so like even small differences here can indicate, you know, differences in water quality. But nevertheless, what we're seeing is that the pH values are fairly similar over most of the range until we get up to the 75th percentile, and then the groundwater in the overburden tends to have higher pHs than the groundwater in the bedrock. And just for the sake of comparison, just putting up the plot that I did before, indicating that there is a kind of a different character to these plots, a greater contrast here, and also that whereas we have the similarities here, the pH is different in the upper end of the range. So that's kind of looking at it parameter by parameter. So here is just a little bit of a rundown, trying to look at things collectively, because the way it turned out is that wells with high TDS also had other characteristics that kind of stood out. So for example, wells that had high TDS and low dissolved oxygen and high pH turned out to be these wells here. And so then there's some consistency there. There's some processes that are going on that are causing multiple distinctions in the water quality parameters. And I guess the other thing that I wanted to mention is that the lowest pH actually occurred in MW1S and PQ4. PQ4 is right in the ore deposit area, and I would say fairly likely is related to geochemical processes related to the ore deposit. By contrast, MW1S is located miles downstream from there, and the cause of the lower pH there is likely not related to the ore deposit. We also looked at temperature, and as we've been talking about, the influence of groundwater in the surface water system is quite important at the Pebble site, and it's related to fish habitat. And so one of the things about groundwater is that it has a mitigating influence on stream temperature. So I just wanted to give you a feel for what that looks like when we compare the air temperature with the stream temperature, and give you a feel for how groundwater is a mitigating influence on temperature. So what I've done here is to take all of the temperature measurements over the multiple years of sampling and divide them into winter, spring, and summer, plot the temperature on the vertical axis here, and each one of these dots represents a data point from one of those seasons. And so what we see here is the air temperature has a very large range compared to groundwater within any one of the seasons. And we also see that there's a large range going from season to season. And in contrast, what you can see in the groundwater is that within any given season, the range of groundwater temperature is quite small, especially when you look at the seasons when there's large ranges in the air temperature. And then the other thing that you see is that the season to season variability is also quite small. And so I'm putting this up here just to illustrate the way in which the groundwater system has a mitigating and stabilizing influence on temperatures of waters that are discharged to streams. So let's talk a little bit about the major ions now, and I'm referring here to calcium, magnesium, sodium, potassium, and the bicarbonate species, and sulfate and chloride. So the reason they're called the major ions is because these are the ions that comprise most of the dissolved solids that are in a groundwater sample. So look first of all at calcium, and we've made our color coding a little bit more complicated now. So 2 shades of blue for the North Fork Cockatoolie, 1 for overburden and bedrock, 2 shades of orange for South Fork Cockatoolie, and 2 shades of green for Upper Tulare. And similar to the other box and whisker plots that I showed you, what we're seeing here is that there's kind of a band within which most of the samples fall, and then there's a few locations that stand out from the others. So the ones that stand out, you'll start to recognize the locations, and maybe I'll save you from me reading them again. Now, the other way that we want to look at the data is to look at the time series. And so what I'm showing you here is the time series of the major ions for MW12S, which is located close to the general ore deposit area. And here, calcium is winning in terms of the concentrations, which is quite typical for groundwater quality. Then magnesium is second, which is also what we expect, and then followed by sodium and potassium at relatively low concentrations. So there is a little bit of seasonality evident in these concentrations, but it's not really terribly pronounced. But we do see a little bit there. So then that means that the SLR people can feel glad that they've made the effort to go out there during each of the seasons, including winter. In MW1D, we see 2 differences. One is that there is a difference in absolute concentrations, and then the other is that in MW1D, we don't really see the same sort of influence in seasonal concentrations. So we can see at some locations there's some influence on seasonality, and at other locations not so much. Another way of looking at water chemistry is to look at groundwater composition. In other words, what is the relative proportion of different parameters in the water as opposed to what are the absolute concentrations. And to do this, we use a diagram called a trilinear Piper diagram. And the quantities plotted on these diagrams are milliequivalents as a percentage of the total milliequivalents. That's a technical term. And I don't think I'm going to do the actual definition of that term, but suffice to say the percentages are representing the percentage of each of those parameters in the water. So I just want to give you a brief rundown on what this diagram, how this diagram works, because otherwise it may be a bit mystifying. So what we do is we have one triangle for the anions, and we plot chloride across the bottom from 0 to 100%, the sulfates across the right side from 0 to 100%, and the carbonate species down the left side from 0 to 100%. Then, for example, if we plot a dot there, that means there's no chloride and no sulfate. It's all carbonate species. A dot here would be 100% chloride, no sulfate or bicarbonate. And then a dot here would be 0% chloride and some carbonate and some sulfate. Then we do another triangle for the cations, and so we've got calcium along the bottom, magnesium along the left, sodium and potassium on the right, and similar sort of thing. This would be 100% calcium, that would be 100% magnesium, like so. So when we do an actual analysis, it might fall in a location something like this. And so then you project the chloride back to this axis in this fashion, the sulfate over to that axis in that fashion, and then the carbonate species over to that axis. And then that tells you what the relative composition of each of these elements is. And what this does is it allows you to distinguish different types of water regardless of the absolute concentrations. So it's nice for being able to see how your water is classified. Then we'll do a separate dot over in the cation area of the diagram, and similar sorts of projections. And then to cap it all off, we will have a sort of a diamond-shaped diagram up here, and where the anions and cations are plotted simultaneously. So then the way that works is you project both of the cation and anion percentages up into this diagram, and then the location of this dot gives you an overall representation of the cation and anion composition of that sample. Clear as mud? So then we project the anions like so, and the chloride is combined with the sulfate, because usually chloride is a relatively small proportion of the anions in shallow groundwaters. And then similarly, the sodium and potassium are combined down here typically, because in shallow groundwaters usually they're a relatively small proportion of the total cations, and also these would have more of a tendency to occur together, and these would have a tendency to occur together. Now, of course, when you're working in different environments, you can modify this diagram according to your needs, but this is appropriate for what we're doing. So this is what it looks like when you actually take all the data and you plot it on one of these diagrams. And again, plotted in this fashion, we're really looking at the big picture. So this is the North Fork, the South Fork, and the Upper Tulare. And what do we see when we look at all this? Well, maybe not much at the moment, but if I try to illuminate things by drawing a few lines on here with what I saw, one of the things that stood out for me is that the range for the cation composition in the North Fork was much tighter than it was in the South Fork and the Upper Tulare. So what I'm doing is I'm drawing parallel lines here that represent an envelope for the cation composition. And we'll also notice that the South Fork and the Upper Tulare are quite similar in the range of composition that we see. And this is not really too surprising, because both the South Fork and the Upper Tulare are draining the deposit area. Now, if I draw the lines the other way and look at the anion composition, then we see a little bit different pattern. We see a relatively narrow range of compositions, basically sulfate poor in the Upper Tulare and the North Fork, whereas in the South Fork we see a certain number of samples in the South Fork are relatively sulfate rich. So these are the wells that are dominated by sulfate. Again, not surprising that many of them are concentrated within the ore deposit area, and then one well further down the South Fork here. Then if we look at a few trace elements, again we have our color coding system here. The NFK overburden is off the top of the screen. It's a light blue, and then again 2 tones of orange and 2 tones of green. And I've added a couple of things to the diagram. One is the ADEC criterion for the parameter, and also the 95 percentile method detection limit for the parameter. And one of the things about analytical chemistry is that when you're sending in multiple samples over time, there are all kinds of different influences on the method detection limit. And so from one sampling event to the next sampling event, you might have a slightly different method detection limit. And so what we did is we looked at all the method detection limits that were that resulted from the analyses that were completed, and to give you a feel for how the concentrations compared with the method detection limit, we plotted the 95th percentile of those detection limits on these diagrams. And so what you're seeing is that there's quite a number of locations where the concentrations of manganese are below the 95th percentile method detection limit. And one of the conventions in dealing with water chemistry is that if it's a non-detected parameter, then the concentration that we work with in the interpretation is half the method detection limit. The other thing that you'll see is that there are a number of samples that are above the ADEC criterion. And we're doing this only to kind of put things in perspective. You know, we're not in a situation where we're trying to meet compliance or anything like that, or characterizing a natural system. And just to put things in perspective, we're just showing the ADEC criterion for comparison. So again, these are the North Fork samples here. These are the South Fork samples here. And those are the Upper Telluric samples there. So then this is the plot for copper. And you can see that for the most part, the copper concentrations are very low. But there are notably a few locations where the concentrations are sneaking above the ADEC criterion. Again, some familiar locations are popping up here. And then this is just a map for 2008, again just showing the geographic locations of these monitoring points. So to summarize the dissolved trace elements then, overall the concentrations are quite low. And of course I didn't show you all of them, and you're probably thankful for that. But the picture is fairly similar when we go through all of the different trace elements. Now, even though the concentrations are generally low, there are notably some naturally occurring concentrations that exceed the most stringent ADEC criterion. And this is just a summary of what that looks like. So I've plotted the number of wells along here and the parameter along here. And you can see that there are lots of parameters where it's 0. And then manganese stands out as the one where there are the most exceedances, and then there are other parameters where there's a few wells where there are exceedances. And finally, some of these exceedances are located several miles from the general deposit area. So to summarize the groundwater overall then, for the index parameters, the total dissolved solids mostly has low concentrations. pH is mostly near neutral. Dissolved oxygen is often near saturation, and the temperature averages about 4 degrees centigrade and is relatively stable. The major ions are generally dominated by calcium and carbonate and typically increase with depth. Nutrients are generally undetectable. With the trace elements, there are a number of elements here that failed the ADEC criterion at selected wells, and that those wells that failed these criterion generally had distinctive index parameters. And then the other thing that we observed when we examined the time histories of the groundwater chemistry, it wasn't always the case, but in general, the water chemistry was relatively stable over time. Something that you don't see in surface water, as you're going to observe in a few minutes. So how am I doing for time? Oh, 10 minutes? I better talk faster. So I'm going to give you a quick overview of the surface water sampling program then. This section of the environmental baseline document was written by Mark Stelgis of SLR. So I'm just representing the results of that work. And I'm going to give you a brief overview of the stream water chemistry, the seeps, and the ponds. So this is a quick look at the stream sampling locations. And you can see that there are many locations located throughout each of the 3 drainages. So I'm going to be looking at the North Fork, the South Fork, the Upper Tulare, and in terms of parameters, again, composition, total dissolved solids, pH, temperature, alkalinity, and copper. Of course, there are many other parameters, but we don't have time to go into those today. So with the water composition, it's a relatively familiar story here compared with groundwater. Again, we saw the greater range in anion composition in the South Fork Cockatoolie and in the Upper Tulare compared to the North Fork. And one thing that's a little bit different than groundwater is that the cation ranges are very similar in each of the 3 catchments. But nevertheless, you can see the impact of the ore deposit on the water composition of the stream samples. Looking at total dissolved solids, this is a very high-level view of the total dissolved solids. I'm just looking at all of the samples that were collected at all of the sampling stations over the period of record in each of the drainages, and representing that with a box and whisker plot. And it doesn't stand out in a huge way on this diagram, but when Mark did his statistical tests that were comparing inter-drainage concentrations, then the total dissolved solids in the Upper Tulare did stand out as being somewhat higher than the other drainages. And so this is the beginning of a story that's saying that the water chemistry in each of the drainages does have distinctive properties. It's not the same across the board in each drainage. Similarly, here you can see that the pH is, for the most part, fairly close to neutral. Again, when Mark did his statistical tests, then the Upper Tulare came out as having a higher pH than the other drainages did. Temperature, it turned out that the statistical testing done here resulted in temperatures that were fairly similar across the board. And what you're seeing here, of course, is the seasonal variation. So even though there's a lot of variation in temperature within each of the drainages, which is what you would expect because of surface water, in terms of inter-drainage comparisons, it works out about the same. With alkalinity, it was back to a similar story as we had with total dissolved solids. Again, alkalinity is at a reasonably low value, but when compared between drainages, then the Upper Tulare turned out with having somewhat higher alkalinity. And then this is the only trace element that I looked at, the only trace element that I'm going to be talking about today, and that's copper. And again, for the most part, fairly low concentrations, but when it came to a comparison, then the South Fork stood out as having somewhat higher concentrations than the other drainages. And then a comparison side by side of dissolved and total copper, and the concentrations of total copper, as you would expect, were somewhat higher than the dissolved copper. So those were the kinds of things that were done in terms of looking at the chemistry and comparing the chemistry between drainages. And so in terms of similar concentrations across drainages, we can say that that was the case for temperature. Hardness was fairly low across all the drainages, although there was some variability. Fluoride, ammonia, antimony, mercury, cyanide was low at all the sites really, and predominantly non-detect, and little spatial variation in many of the water quality parameters that were monitored. On the other hand, there were certain parameters that did vary by drainage, so just to summarize those quickly, as you already saw, total dissolved solids, pH and alkalinity, but also total suspended solids, which I did not present today. And then in terms of the major ions, it included sodium, chloride, hardness, sulfate, and fluoride. One of the nutrients, in other words, in this case, it was the oxidized form of nitrite. It was the total nitrate plus nitrite. And all of the analyzed trace elements except for cadmium and lead. So I did just a quick summary table here. One little summary table of the major ions and one for the trace elements indicating the locations of the highest concentrations. You can see that for the major ions, most of the check marks are in the upper telluric column. And for the trace elements, it's a bit more of a scatter. But suffice to say that it's not in the upper telluric and not in the North Fork either. There are more check marks in the South Fork and sort of an intermediate number of check marks for Cascanac Creek. Now, the other thing that was examined was the variation of concentration along stream and river reaches. And there were some patterns here where the concentrations tended to have a decreasing pattern for total dissolved solids, potassium, sodium, nickel, and sulfate, and there tend to be an increasing pattern for arsenic and chloride. And this particular type of trend was not as noticeable or apparent in the North Fork Cockatoolie River, which is kind of what we would expect because we don't have that source of dissolved solids originating from the ore deposit area for the North Fork. So just some examples here. Just to acquaint you with this plot, this is for total dissolved solids with concentration across the left. There's something called downstream rank here, which is basically the order of the sampling station along the river. So for example, 2 would be near the top of the watershed, and 5 would be close to would be at the bottom of the watershed in this case. So it's simply the order of the sampling station along the river reach. And then on the right-hand side is a plot of the stream flow, just indicating how the median stream flow varies. So what we're looking at here with the dots is the median concentrations, and then the top and the bottom of the whisker represents the upper and lower bounds of 95% of the concentrations that were recorded at each sampling station. So this is how it looks when we look at total dissolved solids for all 3 of the main catchments that we were examining. And as I mentioned, we don't really see a noticeable trend downstream with the North Fork Cockatoolie, but with the South Fork and the Upper Telluric, we do see such a trend of decreasing concentration. Similarly with sulfate, we really don't see very much in the North Fork, but again we see a decreasing trend with the South Fork and the Upper Telluric. And with copper, similar kind of story. Not in the North Fork. We do see it in the South Fork. I just want to note that this sampling point is above the ore deposit area, and then this one is at the ore deposit area. So this actually turns out as a statistically significant decreasing trend. So in terms of those parameters that had decreasing concentrations along the river reach then, we notice it in the South Fork and Upper Tulare for the major ions. That's where we have the most check marks. And then for the trace elements, notice it mostly in the South Fork. Now what about increasing concentrations? So if we look at molybdenum, then there is actually quite a little bit of a difference between different drainages. We'll notice that in the North Fork and the Upper Tulare, there's a trend of increasing concentration, whereas in the South Fork, there's a trend of decreasing concentration. So there are selected parameters for which there are trends of increasing concentration along the river reaches. And as you can see here, there are far fewer check marks for increasing concentrations. So it's saying that in terms of spatial variation along the river reaches, that in most cases we're seeing decreasing concentrations, and in selected instances we're seeing increasing concentrations. Now what about temporal trends? We'll look first of all at alkalinity. And we see that there are seasonal variations here, with the lowest concentrations occurring during periods of spring runoff or fall rains. Similar kind of trend for hardness. And what this is telling us is that the alkalinity and hardness is probably being supplied by groundwater. So during periods when we have stream flow dominated by groundwater discharge, then that's when we have the highest concentrations. In contrast, we're looking at total copper here, and we see that the highest concentrations, generally speaking, are occurring during high flow periods. And so then that's suggesting that the copper in the streams is generally being generated by runoff processes rather than being discharged from the groundwater system. And similar to groundwater, there were a number of parameters that did not satisfy the most stringent ADEC criterion. And it kind of looks like this for each of the three drainages, where there are selected parameters that, have somewhere between maybe 2% and somewhat around 60% of the samples not satisfying the criterion. And you can see that that was also dependent on the drainage. So to summarize the rivers then, there was a drainage-specific water compositions, or in other words, water quality signatures. We can see that there are trends in concentration related to proximity to the ore deposited. In contrast with the groundwater system, there were pronounced seasonal variations in concentrations in the streams, as you would expect. There were some naturally occurring exceedances of applicable regulatory-based limits. And although I didn't present any of the data, one of the things that we noticed is that there was some naturally occurring cyanide in the surface water, which corroborated the results that were found with the trace elements analyzed in the soils and plants. So just a couple more slides here. All right. This is the SEEPS program here. There were selected SEEP stations around the site for analyzing for water quality and monitoring flow. Similar sort of story with the water composition at these SEEP sampling sites. And what we've got here is a plot of total dissolved solids by SEEPs and by drainage. And each one of these bars here represents a sampling location. So what I'm saying is that this blue bar here stacked on top of this green bar stacked on top of this tan colored bar, each of those is a different sampling location, and then this is time along the x-axis here. And so the concentration scale is shown here. And so what we're seeing is that, similar to the surface water and the groundwater, the total dissolved solids for the most part is relatively low. Again, similar to surface water and groundwater, there were some parameters that did not meet the most stringent ADEC criterion. And then that leaves me with about 2 slides regarding the pond sampling program. There were about 40 samples from 28 stations collected across 19 lakes. So it was, compared to the rest of the surface water program, it was relatively minor. And again, there was some dependence of the water composition based on whether it drained the deposit area. Again, there were some exceedances of the ADEC criterion. And one of the things that stood out is that Frying Pan Lake had a different signature parameters than any of the other lakes that were sampled in this program. Thank you very much.
Well, thanks, Hugh. I know that's a very hard subject to cover. There's an awful lot of water quality data, and having done this myself, it's very hard to try and summarize this in a straightforward fashion. So right now we'll take a 15-minute break, and then we'll be back for panel review and discussion.